Okay, this will be part 2 of the video series on the integrals of the 6 basic trig functions. And if you haven't done it yet, I would definitely watch the first 2 videos because they'll show where these formulas came from. And in the part 2 video, we looked at some example problems using indefinite integrals. And in this video, we'll look at 2 more sample problems using definite integrals. But again, just a reminder, the derivatives of the 6 trig functions are on the left. Integrals of the functions are on the right. So with that in mind, let's try a problem. Okay, now in this first problem, you want to find the integral of the cotangent of x from pi divided by 6 to pi divided by 4. And again, you don't need U-substitution on this one because it's just a simple x. If it were anything other than a simple x, we'll have to use U-substitution, which we'll do in the second example. So what I'll do in this is I just want to find out what this is equal to. So it's going to be equal to. And then to actually see what the integral is, let's go back to the list of formulas. And what happens is we've got the cotangent. So the integral of the cotangent is equal to the natural log of the sine. So we'll use that. So this is going to be, we'll put brackets around this. This will turn into the natural log of the absolute value of the sine of x evaluated from pi divided by 6 to pi divided by 4. And again, this would be just like any other definite integral, so just plug in the top number and plug in the bottom number. So what this is going to give you would be, put it in brackets again, the natural log of the absolute value of the sine of pi divided by 4, and then subtract from that the natural log, and this time plug in a pi divided by 6. This will be the integral of the sine of pi divided by 6. So it looks like that. Now the next thing you want to do is actually figure out, we want exact answers on this. So you got to find out what is the sine of pi divided by 4. And I usually recommend just kind of drawing a picture of this thing. So what I'm going to do is draw a circle over here. Looks like this. And I'll actually draw a picture of a pi divided by 4 angle right here. Now, within this circle, pi divided by 4 is a 45-degree angle, so the triangle would look like this. It goes up, here, here, and here. So label the sides. This side would be 1, 1, and the square root of 2. Now I'll do the same thing for a pi divided by 6 angle. So I come over here and I'll draw another circle and draw a picture of this angle. This angle is pi divided by 6, and what it's going to look like if you do the triangle, pi divided by 6 would be a 30-degree angle, so it'll look like that. So this side would be 2, 1, and this side would be square root of 3. So with that in mind, it makes it a little bit easier to turn these things into actual numbers. So now what you've got is this. This would be the natural log of, now remember the sine is y over r, so the sine is going to be y over r. So looking at this picture, it would be 1 over the square root of 2. So this will turn into 1 over the square root of 2. Then you've got minus this one, which would be the natural log of, and the sine of pi divided by 6, again, would be y over r. So in this one, it's going to be 1/2. And then I can go ahead and get rid of the brackets here. So this will turn into the natural log, the absolute value of 1 over square root of 2, minus the natural log of 1/2. Now actually that would be the answer right there. If you put this on a calculator, it would turn out to be about 0.347. So if you wanted a decimal answer, it would turn into approximately that. Well, there's the process right there. So it's really just a matter of using the integral rules. You start with the cotangent, use the integral rules. The integral of the cotangent is the natural log of the sine, so there's the formula. And then it's just a matter of plugging in the numbers, getting a picture of the angles so that you can get the exact sides, and there's the answer. So what that is, that's a sample of a definite integral that did not involve U-substitution. Now let's take a little trickier example that does involve U-substitution. Okay, now in this example, this one's going to require U-substitution because we have something more complicated than just a simple x here. But there's also some other work you have to do on this one too. When you first look at this, if you looked at your rules, the rules would look like this. There's nothing in this list of integrals that matches up with this exact problem, so you're going to have to do some preliminary work to try to turn it into something in that form. So what we'll do is this, and the trick on this one begins with a trig identity. Now you might remember that 1 plus the cotangent squared is equal to the cosecant squared. So we'll take advantage of that to try to turn this complicated problem into something that's in our list. So what that's going to look like would be this. This is going to be, I'll make it be the integral from pi divided by 6 to pi divided by 4. And we'll turn this into 1 plus the cotangent squared will turn into the cosecant squared. So this will become the cosecant squared of 2x. And then dx out here. Now the next thing, take advantage of the fact that you've got the square root of something squared. Those will cancel out and leave you with this. This will be the integral from pi divided by 6 to pi divided by 4. And the square and the square root cancel out and leave you with the cosecant of 2x dx. Now what this does, let's go back and take a look at the rules. What you've done is now you've changed it from a problem that didn't fit into something that does. So you have a rule here for the integral of the cosecant of x, and it'll turn into the negative of the natural log of cosecant plus cotangent. So we'll take advantage of that, but again you have a little more work here to do first. Because this is more complicated than just a simple x, you're going to have to use U-substitution. So in the U-substitution, we'll try to change this dx into a du, and we'll do our U-substitution over here. And it's going to be just like any other U-substitution that you've ever done. So first of all, we'll let u be equal to 2x. So that means that du dx would be equal to 2. So that means that the differential of u would be equal to 2 dx. And again, you need a dx, so we'll move the 1/2 to the other side, make this be 1/2 du will be equal to dx. Now in the U-substitution, here's a dx here. You match it up with this dx, and when you substitute it, you'll substitute this right here. So that's going to be the U-substitution, and again, we'll stick a little box around that just to isolate it. So there's the U-substitution right there. Now what that does, that turns it into this. That'll turn it into the integral. We'll put it right here. The integral, and this will become the cosecant of u. And in place of dx, we'll put what dx is equal to, which would be 1/2 du. So this is going to be a 1/2 du. Now you've got one more thing that you need to take care of here, and I think we'll do this one in blue. This goes from x equals to x equals. Here are your limits in terms of x. So you have to do one more thing, and that's to change the limits from x limits into u limits. So what that would be this. We'll put this over here again. So when x is equal to the top one, pi divided by 4, then what is u? Then u would be equal to, and take the pi divided by 4 and plug it into this right here. So this would be twice pi divided by 4, which would give you pi divided by 2. Now figure it out for the bottom limit. So when x is equal to pi divided by 6, then u would be equal to, and again plug it into this one, u would be equal to twice pi divided by 6, which gives you pi divided by 3. Pi divided by 3. So what this is, here's the limits. Let's just go ahead and stick a little box around these two just to isolate them. So we'll go around this one. And what this was, this is where you changed your limits. So you had to do a U-substitution and also change the limits. So what that gets you to is this. Now, when x is equal to pi divided by 4, u is equal to pi divided by 2, so now you've got a pi divided by 2 right there. When x is pi divided by 6, u is pi divided by 3, so you've got a pi divided by 3 right there. So now we're ready to go on with the problem. We've completed the U substitution. Okay, so what this one's going to be equal to then would be this. You'll now need to go, and actually we can do one more thing here first. We can go ahead and bring this 1/2 out in front. So this would be 1/2 of the integral of from pi divided by 3 to pi divided by 2 of the cosecant of u du. Now, using the integral formula, we'll make that be 1/2, and put this right in brackets. And to find the integral formula, you go back to your list of rules. So you're looking for the antiderivative of the cosecant, and using the rules, the antiderivative of the cosecant, it's the negative of the natural log of the cosecant plus the cotangent. So we'll use that. So this will become the negative of the natural log of the absolute value of the cosecant of u plus the cotangent of u. And then put brackets around that, and we'll evaluate that from pi divided by 3 on the bottom to pi divided by 2 on the top. Okay, now plugging things in, it will look like this. This will be equal to 1/2, and we'll put brackets around this. Now, first of all, plug a pi divided by 2 into both of these. So again, this is just going to be standard plugging in the top and the bottom one. You've got the negative of the natural log of the absolute value of the cosecant, and plug in the pi divided by 2, plus the cotangent of pi divided by 2. And I'll put brackets around those. So what that is this thing evaluated at the top number, then you have minus this thing evaluated at the bottom number. So the negative of the natural log of the cosecant of pi divided by 3 plus the cotangent of pi divided by 3. So plug in the top number, plug in the bottom number. And then we'll put brackets around the whole thing. And in some cases, the trickiest part of this is just trying to find the exact value of these numbers. Okay, so what I've got here is I want to find the exact values of pi divided by 2 and pi divided by 3. So just like we did in that last problem, I'm going to go ahead and draw a circle and get a picture of each one of those angles. So this will be the circle for, and the angle, let's draw a picture of pi divided by 2. And then over here I'll draw one for pi divided by 3. So here's another circle. And this is what pi divided by 3 will look like. Okay. Now, first of all, pi divided by 2 is a 90-degree angle, so that's going to go straight up like that. If it goes straight up, that means that there is no x, so x would be equal to 0. Y would be equal to 1, and we'll consider that r, the radius, would be 1. So that's x, y, and r for a pi divided by 2 angle. If you have a pi divided by 3 angle, that's a 60-degree angle, and it would look something like this. So this is going to be 2, 1, and the square root of 3. So now you've got all the sides that you need to make this thing exact. So now we'll come back down here again. This is going to be minus the natural log of, now the cosecant of pi divided by 2, just a reminder on these, the cosecant is r over y. So r over y. So for pi divided by 2, r over y would be 1 over 1. So that will turn into a 1. And then you've got plus the cotangent of pi divided by 2. And the cotangent of pi divided by 2 is x over y. So that would be 0 over 1, which will give you 0. So there's the first one right there. Then you've got a minus, and again, I think I'll stick this in brackets just to keep them separated. So this one should have been in a set of brackets here. You've got that. Then you've got minus. Now let's do this one. It's going to be, and again, we'll put its own brackets, the negative, the natural log, and we'll do the same thing again. The cosecant of pi divided by 3, so this time we'll look at this angle. And the cosecant, again, is r over y, so that's going to be r over y. So looking at this picture, r over y would be 2 over the square root of 3. So this one's going to turn into, down here, 2 over square root of 3. Then you've got plus. Now, the cotangent would be x over y. So again, look at this picture. X over y would be 1 over the square root of 3. So you've got 1 over square root of 3. So a lot of times the trickiest part is just turning the trig stuff into its actual numbers. So it looks like that. So I think we'll put it down here now and keep going. That's going to give you 1/2 of, let's watch how these work. This one will turn into actually the negative of the natural log of 1 minus, and this one will turn into the negative of the natural log of, now you can add these together. Both of them are over the square root of 3, so this would be 3 over the square root of 3. So this will turn into 3 over the square root of 3. So there's that one, and we'll put brackets around all this. Now just a couple things here you might remember from your log rules. The natural log of 1 is equal to 0. So this term right here will completely disappear. This whole term goes to 0. So what that gives you, you've got the 1/2. Actually, now you can do this. 2 negatives make a positive. You're going to multiply it times 1/2. So this will turn into 1/2 of the natural log. But remember, 3 divided by the square root of 3 turns into, it's like multiplying both the top and the bottom by the square root of 3. This will actually turn into the square root of 3. And that will actually wind up being the answer to the problem. So square root of 3. So 1/2 natural log is square root of 3. Now if you were to actually stick this on a calculator, it turns into about 0.275. So, but anyway, that's going to be the exact answer. So just kind of run through the process again. The first thing to do is use identities to change it into something that you can find an integral for in this list. So looking at your list, you started out with a problem that didn't match up, but you turned it into a cosecant problem, and that cosecant does match up with something in this list. Then from there, it's just a matter of doing U-Substitution. You have to change the limits. Once you get the problem set up, then you want the exact answer. So I like to draw these little circles where I can come up with the square root of 2, square root of 3, everything you need for exact answers. Then it's just a matter of running through the algebra. When you finally get finished, it'll turn out to be this answer right here. So that's an example of how to use the trig integrals. In the first example, let's go back to it again. The first example just had a simple x, so it did not require U-substitution. This second problem had something more than just a simple x, so you had to use U-substitution. It takes a little bit more work. So anyway, there's a couple of examples using definite integrals and the integrals of the trig functions.